All right, let's get started. Let's see, where was I? Yeah. All right. And let's just say hi. Okay. All right. So this is another stream. Today is going to be a bit different. We are going to be exploring GPU computing. This is something that's completely new. I've actually never, sort of done anything like this. So it's pretty new for me as well. Let me just close a couple of things. Maybe I'll keep this up. Yeah, so it's pretty new to me as well. It's something that I've been meaning to pick up because of a few embedded projects that require, some expertise in GPU computing, etc. So I thought I'd make a quick live stream on this, and this is going to be, this is going to be a short one, but let's get started quickly. So the first thing that I'd like to actually talk about today is can get to some of the basics, which is what, when we talk about GPU computing, at least what do I understand, after having sort of been through quite a bit of material at the moment. So, I'll get to all the entire landscape and all the different complexities around portability, etc. when you are trying to program a GPU. But specifically, I'll sort of just constrain our, this particular stream to using the GPU for specifically compute. So the GPU can be used, or rather it's, it was built to actually sort of render graphics on your screen, which could be your UIs, your games, anything that's visual, and you actually want those pixels to be displayed on your screen. There's a lot of work that happens to get those pixels on screen. That's the primary, that was why, the GPU was built. But I think over the last decade or so, GPUs have moved into, have become more useful. And that's where this whole idea of general purpose GPU computing comes into the picture. So let's talk about that particular portion, which is GPU computing, not the graphics rendering portion. Of course, that's great, but that's not something that we're looking at today. The reason we're looking at the GPU computing piece is because of its applications in compute, things like numerical analysis, a large data sets need to be crunched through, but a lot of the data that you need to go through, a lot of these operations can be are actually parallel. For example, you want to add like two vectors, or you want to multiply two matrices, or you want to basically crunch some tensors for machine learning, etc. The GPU being an highly parallelizable, you can say thing, we could make use of that for such parallel computation. Now, with that said, let's quickly get into the place where we see what, when you think of the GPU, what actually you should be thinking about. So this document by Apple was pretty good. I thought I'd put some presentation together, but I didn't really need it because this makes sense. Well, sort of anyway, the link is up here. I'll put it in the description anyway. But so effectively, you can think of the GPU as the diagram shows over here. Quick check. I hope everyone can see this. Let's check the chat. Yeah. Is the screen legible? Or do you want it to be bigger? All right, cool. So it is, all right. So it's very simple. I mean, obviously it's not very simple, but at least to build from an introductory perspective, if you want to build a mental model, here's how you can think about the GPU. So the GPU is like a server, and the application that uses the GPU can be thought of as the client. So in this case, what you're seeing is there's something called metal. So to sort of talk about, because we're anyway talking about this, we talk about what metal is. So every OS provider, or at least the most popular ones, which is Windows, Mac, and Linux, they have, obviously they've got they build PCs and they build computers, and those computers are running their own operating systems, and the operating system in some way has to communicate with the GPU. Usually that's the GPU driver that's communicating with the GPU. But in order to sort of interface with the GPU driver itself, you want some sort of some sort of an API built on top of that. Those OS native APIs are what you can also use to sort of talk to the GPU and get your work done. And the one in Apple is called Metal. It's the Metal API that you can use to effectively talk to Apple GPUs. That is the current crop of Apple Silicon M1 GPUs as well. And so let's say you were using a PC and you have an NVIDIA graphics card, the same thing applies. You have NVIDIA graphics drivers or different kinds of other drivers. But basically you want to interface with that so that you can communicate with the GPU. And in Windows, that's the native one is DirectX. And in Linux, I believe you use something called Vulkan, etc. Well, anyway, that's how much I've been able to sort of gather at this point. But anyway, all in all, you can think of your applications sending requests. These are usually commands to the GPU, and the GPU responding with a response, right? That's a very high level oversimplified view of how you can think about things, but in practice it also feels like that. So just a heads up on that. That's what you can think of. Now the next thing is the GPU. How do you send these commands? Now that's the whole piece. How are these commands or requests sent over to the GPU, and how are the responses coming back? Now the complexity in all of that is what is basically GPU programming. And specifically when you use the GPU not for real-time graphics rendering, which is playing a game, or the UI on your machine, which is what are you looking at right now, if it's not for that, then you could pretty much use your machine for, if you have a lot of computation that you want to do, that's by it's actually pretty much, you could think of a way of parallelizing it. Then you could pretty much use your GPU if you want to use the raw horsepower to do parallel computation. All right. So the CPU is very good at latency sensitive work that you want to do. That is, you want to do something very quickly, you want a response. The CPU, the architecture has been evolving over a number of years to basically to cater to latency, whereas GPUs are catering to mostly throughput. You throw in a large amount of data and say, okay, do these parallel calculations at the same time on this piece of data. So the simplest way I can sort of explain this is, let's say you have a large array of 1 million elements in the array, and you want to go ahead and actually let's say you want to just find the cube root, you want to find the square of each element in that array. Inherently, that's, you can actually parallelize that, right? Because there's no data dependencies. You can pick one element, square it, put it back, or rather create another array and put it in there, whichever goes for you. But basically, that entire operation can actually be parallelized. That's what we mean by parallelizable operations or workloads. Not everything is parallel. If there are dependencies, then there are dependencies. But a lot of stuff is actually, can be parallelized, and that's what we're talking about today, right? So let's take a pause on that. Any questions on that? Okay, I guess not. So the next step is you're sending commands through, and I talked about how were these commands actually sent. So I won't be getting into what the command looks like right now, at least, but think about the command as, let's say I want you to, basically perform this calculation for me. I'm going to put that, not the actual, code that says, do this calculation this way, but I'm going to say, here are the inputs and here's the output where I want you to output whatever your result is. Here, I'm going to put it in a command, and I'm going to put it in something called a command buffer. So the command buffer is like this, it's a buffer basically. So you put your commands in there, and then you send it off to the GPU. And then at the GPU, this is like the one image where it sort of captures everything to build a mental model, at least. So the metal app is building commands, or rather it's constructing commands, and it's sort of, packaging those commands into a command buffer and then shipping that off to the GPU. And the GPU has this thing called shader code. Shader code is nothing but code that runs on the GPU. All right. Now there's quite a bit of history as to why it is called shaders and all. I haven't actually been able to clearly pinpoint why, but anyway, it was called shader at one point because it was doing some shading work. So the name stuck, I believe. I don't know how much of that is true, but anyway, that's not important. The idea is shader code is code that runs on your GPU. That means your GPU specifically executes that code, and that code is called shader code. The important thing that we need to keep in mind is, of course, the app constructs its commands and sends them over, but the GPU needs to be configured to say, okay, run this particular code on these commands that are coming in, right? The commands are actually things like, draw this, compute this. There's also something called blit, but which is here, but we're not talking about that. So basically, we need to do two things. We need to be constructing these commands, and we also need to be sort of configuring the GPU to say that, okay, here's the shader code, and here's how I want you to process all of the inputs that I'll be sending your way, right? Does that roughly make sense? Okay. I assume that does make sense. Okay. So basically, you have your application. That's your GPU driven application, and then you have your GPU. You send commands to the GPU. The way you send them is you package them, put them in a command buffer, ship them off. But before you ship them off, you ensure that the GPU is configured in such a way that it knows exactly what to do with these commands. Now, these operations are what effectively what we say when we talk about GPU computing, right? And some of these points are mentioned over here. There's a little more detail in the pictures, etc. The way you construct those commands is you build something called a command encoder, and the command encoder knows how to construct these commands for your specific GPU, and you can sort of keep going through that, like keep spitting out commands that are packaged up and sent to the GPU. So commands that are packaged up and sent to the GPU are not immediately executed. They're actually put in something called a command queue, right? And that command queue is Yeah, so basically you can think of this as the command queue over here, right? It's put in the command queue, and as and when the GPU is done with work, the previous work that was submitted, it keeps picking stuff up from the queue, and it keeps going forward, crunching through. As long as there's work, it keeps going through. Okay? Makes sense, right? Okay. Yeah. I guess that makes sense, yes. So that is basically called the pipeline. Okay? That's called the pipeline. So the pipeline is, actually, let me correct that. The command queue is where is the queue to which you submit your commands. The pipeline is something that you've configured your GPU in such a way that all these commands sort of go through your GPU, get processed in a certain manner. Like, for example, you apply this shader code at this stage, then you apply the next shader code at the next stage. So you want to create a pipeline to say, okay, when, what to do, right? Because not all calculations are, the same. The best example that I can give you is, let's say you have, let's take the example of, let's take a simple example. Let's say that you want to do vector multiplication, and then you want to do something like, you want to go ahead and take the, you want to take the root, or rather not the root. You want to square your numbers. Like, you want to do two separate things, right? So you can actually have two pieces of shader code where one does this multiplication first, and the second one actually does the, the raising to the power of 2. Of course, that's very simple, but that's not how it's done. But just to give you an example, so you can actually build a pipeline saying that all of your inputs that you're sending through as commands will go through, these shaders in this order, right? That's the pipeline, right? Okay, so now enough with that. What we are going to be focusing on is what's called WebGPU. Let me actually sort of go there. So WebGPU, if you actually go to the main site, you'll see that it's a safe, portable graphics library for Rust based on the WebGPU API. So WebGPU, that is WebGPU, is an actual standard. Okay, WGPU is the crate that the community has built in Rust that implements the WebGPU standard or API. And the idea is it does both, as I said, which is graphics rendering. Predominantly, a lot of stuff has been, like, for example, if you just scroll down, all of this stuff has been written using WebGPU. Like, there's a game engine called Bevy. There's a game that's called Valorant. There's, some GPU fluidics solver, which is basically simulating fluid movement, which is quite difficult, actually. And then there's a whole bunch of things, a whole bunch of projects that people have worked on. These are all examples of what you can do with WebGPU. And a lot of this stuff is all mostly focused on the rendering side. There's not a lot of stuff, to be frank, when we talk about GPU computing using the WebGPU standard. And that's what we're going to talk about today. We're not going to, because even I don't know a lot. I just started this stuff. I've picked up a few things, so I thought I'd just sort of learn, and for the benefit of everyone, share. So, and the other part is, as I said, applications that are using WebGPU, they can run natively on Vulkan, which is that API that probably Linux uses, Metal, which is macOS, DirectX, which is what Windows uses. And then OpenGL is another one, which is, I believe, sort of the replacement. WebGPU is the replacement for OpenGL. Now, the different places are giving us different information, but I'm not going to get into that. But effectively, you can say that WebGPU is like a modern graphics API that you can use for, both compute as well as rendering. And the other thing is, you could also go ahead and directly compile to WebAssembly, because obviously you're writing in Rust. You can go ahead and, sort of just take your application, whatever you've built, and compile it to WebAssembly. So the first thing is WebGPU was actually built for the web. And then naturally, once it's built for the web, it seems to find its way out of the web. So it's now available, as, for example, for native applications that are using WebGPU. Sorry. Yeah, I hope that little, sort of little piece of information makes sense. Because even I found that there's a lot of stuff. There's a lot of evolutionary stuff that has been discussed so far. For folks who may not know anything, there's a lot of stuff that's happened in the past. And this word that they use, safe and portable, it is actually quite a lot of work to get that done. Not easy, because you need to be able to use the same API across these different platforms with different operating systems and drivers and features and capabilities of the cards, etc. That's quite a tall order. At the same time, you also want the API to be safe. And that's where the whole Rust piece comes in, which I will talk about as well. Okay, so far, so good. Everybody with me? Yep. Any questions so far? Yeah, I mean, I'm pretty sure this whole thing can be like, what is going on? Because that's exactly how I felt anyway. Okay, anyway, I'll just keep moving now. So now that we at least have like a very, very basic idea of what a GPU is, how would one go about programming a GPU, and how one could use it specifically in the context of computing on the GPU. Now, let me actually jump into this WebGPU. So we're going to use that. So I've actually done a little bit of work already, just to save time again. So I've pulled in, I've sort of, cobbled together lots of information from different places and put together a small, project that for demonstration. Doesn't do anything more than that, just to sort of walk us through what we can get. So the first thing that I want to walk you through is, what we're using, as always, the dependencies that we're using. We're going to be using WebGPU. As you can see, it's not even 1.0. It's still, by the way, with the WebGPU standard, if you want to look at it, the actual standard, it's available, it's published. So this is the complete standard that is published today. You can go ahead and look at that. There's a lot of information in here. It's years worth of information and mistakes and things that people have been, I guess, collecting and building on top of. But anyway, so the actual standard is over here. It helps when you're actually reading the WebGPU or the WGPU crate. It helps a lot because you sort of try to understand why WGPU is written this way and not the other way. So that's the first crate. Then obviously there's some amount of async stuff that you use over here. There's a very subtle difference over here when we talk about your usual async await using just the CPU versus what the GPU is. Yes, the GPU is a very highly asynchronous heterogeneous computing model that we're going to be talking about, but it's very different. It's different. In other words, you're not going to actually call async await and your code that's running on the GPU is going to do any async await. No, that's not the case. We'll talk about that then. The other cases, except this one, which is Rayon. So I was trying to do some tests, and funny enough, I don't know what I'm doing wrong. I think I need more clarification on this. But at least the calculations that I'm doing right now, the CPU seems to be faster for some reason. And I don't know if it's the machine that I'm using or if it's generally the case, etc. I'm not too not too sure about that. I need some clarification on that. But before we get to that point, I just wanted to say that there are two important things over here. One is called WGPU, which is the crate that implements the WebGPU standard. And then Rayon, which maybe we'll do in a separate talk. That one I'm a little more well versed with, which is basically Rayon deals with, actually you can sort of take a look at it. Rayon, Rust. So this is a library that is written primarily to, for if you want data parallelism in your code on the CPU, you use Rayon, right? Forget about GPUs. You just want to talk about the CPU and you say, look, I've got all these cores, I've got 8 cores or whatever, and I'd like to parallel my computation can be parallelized on these cores because they don't have a lot of data dependencies on each other, etc. Then this is the crate to use. It's very, very intuitive because I'll just show you. The way they've actually developed this is very good because you don't really do much. The way you've been programming in non-parallel programming environments like your regular Rust versus this, it's almost a drop-in. You don't have to do much. All right. So that makes sense. Let me just check the chat. Any questions? Okay. All right, I hear somebody's actually calling me on Teams. I don't know who that is, but fine. Okay, so those two crates make sense because we're going to actually only be talking about those two, not anything else, right? Okay, so what I've done is I'm actually going to write the code and walk you through it, step by step. So let's create a new example, new file. So I'm just going to call this vector edition, or I'll just call this vector edition and I'll say rs. So I've already done some of the work, so I'll sort of walk you through that. If you're not following, just sort of let me know. All right, and I take a lot of time to write code because I'm not a developer. Anyway, so let's say so the way this is going to work is some of these calls are going to be async. So let me actually write the main function. So what I want to do is I want to basically go ahead and set up the framework that I put together. The framework does all the setup of what we need to do. Remember, I talked about the pipeline, the command encoder, being able to construct the commands. All of that is something that I just do it in my framework. So that's an async function. So let me just go ahead and say, I'll just call this run GPU, and for now we'll just say let's make that empty. So let's say let framework is equal to I'll just call this default for now. All right. As I said, this is an async function, so that's kind of what's expected. Now, I will sort of walk you through what a framework is, etc., a little more. But just in case I'm not able to complete this, I actually have written this, so I'll walk you through that anyway. And then let shader is I'm just going to go through this. So here you see something which is we've got, I'll show you the shader code as well. The shader code is what is called. So let me just show you the shader code. Where's that? Okay. So the shader code that you write, this is the code that actually runs on the GPU. Okay. Now, just to sort of walk you through this, it's very C or C++ like, I'm being told. I don't know C++. It does look a little bit like C. Fine. So here you basically define a type, which is a vector. You're saying that it's an array of U32s, and I'm going to label that data, one of the fields in there, and I create 3 of them. All right, vector A, B, C. 2 of them are for input, the third one is output. And most of GPU computing is you give it some input, it does that parallel computation, then spits it out in the output, and then you're done. Right? And then what you see over here is, this is the part where WebGPU actually helps us with. So these are called bindings. Okay. Now, the best way to actually talk about, I'll get to that part a little later, but these are called bindings. And now bindings are, you can think of bindings as resources that your shader code requires to perform the calculation. In the simplest way I can say, your buffers, like you've got a large buffer of 1 million elements or whatever that is, you want to compute something, right? Now that's a resource. You're saying basically with this statement, you're saying that I want you to put that resource or group that resource into this group called 0. And I want that this particular buffer, which is buffer, what let's call that A, to be bound to vector A. So when I allocate it in GPU memory, I want this type to be using that buffer. Okay? I hope that makes sense. Okay, let me just check the chat. Right? Yeah, I guess that makes sense. Okay, so let me go back. And this is what your shader code looks like. It is doing nothing, at least in this. I've just been trying this out. All it does is takes one element from vector A, one element from vector B, and basically multiplies that and puts that in vector C. Then there's this thing called global ID and all of that, which I will try and show you what's going on over here. The other thing that you see is it's got @compute. @compute basically means you are trying to compute. You're basically using this for GPU computation and not the rendering part of things, right? And work group size is what, maybe I can just spend quickly 2 minutes on that so that, I don't lose you guys. So the other thing is NVIDIA's documentation and model is actually very good, and people use that a lot, and that's actually helping quite a bit. Let me see if I can find any proper image. Okay, yeah, this looks like it. Well, let me just take this. Okay, I hope everyone can see this. Yeah, can you guys see this? Sorry, can you guys see the picture, which is the host and the device? I guess you can. So this is the device, in this case is the GPU. The host in this case is the CPU. The host does what's called launching kernels. What you just saw, which is this thing, is also called a kernel. It's also called the shader code, right? That is launched onto the GPU. And the way what the GPU actually looks like is it's got a bunch of blocks. And within each block, there are a number of threads or cores. Okay, so that's the difference between a traditional CPU and a GPU. Traditional CPU, you might think of something like 8 core, 16 core, etc. But in a GPU, you can have hundreds of cores, right? And that's where this whole parallelism comes into the picture, right? So you can launch one kernel, and basically, let's say this kernel is launched in such a way that this block of threads is going to, each thread is one core, right? They want to start executing, take up whatever data you've passed in, and then they'll start executing. That makes the whole thing very, very parallel, right? So this is another, sort of view of the same thing, right? These cores, all these little cores that you see in green, they are the ones that are doing the actual, they are what you call the arithmetic logic units that are actually doing the computation, which is all simple computations, right? That's what you need to keep in mind. And the work group is primarily talking about those things, saying, okay, if you're going to launch a kernel, I just want to know how many threads do you want me to go ahead and spool up, or rather activate for you for this particular piece of work, right? Okay, so that makes sense. Now, where was I? Yeah. So basically, I go ahead and pull this up, and I'm just going to go ahead and say, okay, fine. I want my shader code from here. Say what? Why are you throwing an argument? Oh, sorry. I forgot to pass the argument. Okay, so I have my framework, I have my shader. The shader code is what I've just shown you right now. Then the next thing I need to do is basically create some buffers, which is these buffers are your regular buffers, but then I'd like to go ahead and create GPU buffers out of them. So in order to do that, I'm just going to do something very simple. I'm going to say, let's say size equals, I want a buffer that, let's just start with 10,000, okay, elements, 10,000 elements. Then let's say I want vector A to have about yeah, let's just go with the so if I say I'll just say I want two vectors, which is one is an input and an output. Right? But basically, I'd like to go ahead and actually create some. Let me do it this way then. So let me say 0 to size, start into it here. By the way, this is the functional programming aspect of Rust that you all probably know by now. So let's just call this, I'm going to iterate over this, then I'm going to go ahead and yeah, I can just do select into a vec. Okay, so this should be very simple. The other thing that I could also do is, just for the benefit of everyone, let me try this, which is not this way. Let me try a dot clone, sorry, dot so that's the one, right? No. So a dot clone, and I'd like to go ahead and say Twitter dot reverse dot collect. Sorry. Sorry, keep missing this. Okay. Right, so I have my two vectors here, and these two are basically, one is 10,000 elements, the other one is reversed, right? I've just put them in two vectors, so I have my two vectors. Now, these three are all what you call what is that? Yeah, these three are, as you know, these are all allocated in your system memory. You can just say that. This is your regular system memory or your RAM where these buffers are being allocated. Then the next one that I want to create is I want to create a buffer with capacity, and the capacity is basically size as U64. Right. I just want to create a vector with that size. And what's your problem now? Oh, sorry. Okay. Yeah, it's going to need a type. Okay. I'll sort of leave it there for now because I think I know what to do next. Then now I want to use this to sort of say I want to create my GPU buffers from this. So the way I'm going to do that is I just call this GPU A and I say let GPU buffer from slice sorry, you can say a dot as slice. Right, so this gives me my GPU buffer. So I'm basically, what I've done is I've simply gone ahead and taken up, I've basically gone ahead and used the host allocated buffers, use them to construct my GPU buffers. You can think of them as, I created a copy of my host allocated buffer on my GPU. Okay. But, okay, I don't want to confuse you, but yeah, you can just think of it that way right now, at least. And when I do b.addSlice, I hate this keyboard. The same thing. Okay. So we're doing all of this. Ultimately, what's our goal? We want to take those 10,000 elements. We basically want to multiply, in this case, we want to add those two elements, and they should sort of give me a third vector, which has all of these elements added up. That's all we want to do. And we want to do it on the GPU, not on the CPU, right? That's what we want to do. I hope that's making sense. Any questions? So let me ask. All right, let me say GPU, output. Let me say that is GPU from buffer, right? No, I don't have a slice here. So I can go ahead and do the dot. Yeah, the dot is. Okay. Yeah, this is going to throw that error. All right. Okay, so we've got our 3 buffers over there, and we've got our 3 buffers over here. Now, all we need to do is go ahead and do the computation. The way we are going to do that is we'd want to go ahead and basically construct our command. In order to construct our command, we need the command encoder. And the way you construct a command, you don't actually get into the nitty-gritties of WGPU and sort of start figuring things out, etc. Because most of the framework that I've written over here, which is both the kernel and the framework, they already sort of provide the options. So before I actually go ahead and start using the buffers, I need to, as I said, I have this shader code. I need to bind my buffers to the shader code. In order to do that, I've already written some stuff, so I can just go ahead and say bind group. Let me just say bind group. So I create my bind group. In order to create my bind group, I'm just going to say go ahead and what was that, by the way? Yeah, create my descriptor set. So I create my descriptor set, and then I basically start binding my buffers. The way I bind my buffer is, I've already got the buffer, which is the GPU buffer that I created. So I provide that GPU buffer in, and this I believe is probably in. And then I need a usage. Usage is particularly of, I'll just explain that. Usage, as you can see here, is, now this is the other thing about that safe part that we were talking about in WGPU. We were saying that the WGPU crate is a safe and portable API, right? So a lot of the things where you normally make mistakes, for example, you don't want to use this buffer for writing, you just want to read it, right? There's no need. For example, in this, when I created this buffer, I've created a buffer that says, look, there's an element, there's 10,000 elements in here, and then there's 10,000 elements in B. I want you to add them both up and put the result of that in another buffer called C, right? Now, the first 2 buffers, which is A and B, you don't need to actually modify them in any way. So all you need is read access to those buffers, and you want to ensure that that invariant is maintained. And the way you sort of do that is, with using the WGPU API, you have to explicitly say, okay, how are you going to use this buffer? Are you only going to read it? Are you going to write to it? All of that. Okay. Now, and then you also bind all the other buffers as well, which is same thing, which is GPU B. Okay, let me just put that slide. Okay. So, and then you got your GPU output, which needs to be. Now, this one is actually a little different. You're going to need. This one is going to be written to, right? So you're going to need to look at it differently, which means you need read write both, right? I hope that makes sense. Yeah. Okay. Yes, I believe. I was hoping to keep this under 1, but seems to be stretching out. Anyway, let's just sort of go through this so that we can sort of come back. Now that I've bound my buffers, the next piece is I want to go ahead and basically create my shader code and tell the GPU that here's how I want you to execute that shader code, right? So in order to do that, I've created a type called program. This is. So I want to create, basically I add my shader here, and the shader is the entry point, which in my case, as you know, is main. So you see, it's the main function, just so that you know. And then I'm going to add my descriptor, which is what I just created, which is my bind group. Okay, what's your problem? All right, fine. All right, now I have my program. Now I use my program to effectively create that pipeline that I was talking about. And then the commands can now be encoded, and then you can go ahead and submit those commands to the queue, right? Those are the steps that you sort of need to go through in order to sort of flip this through. Now, in the interest of time, I think we're sort of heading into the 1 because I do have another appointment that I need to be at. I'll just sort of walk you through a pre-prepared example, just so that you have the complete text and you're not left hanging. So let me switch, and I'll also show you the implementation of things. All right, so this is a little more cleaner, so because everything's done. So far, you just saw that we were creating our framework, we created our shader, we went ahead and created our buffers and our bindings. All of that you just saw. Then we created something called the program, which is what so the way we've done this is the program contains your shader code, and it also specifies the entry point. And this shader is going to be using these inputs and these outputs. That's what this program type holds. That's the information that it holds. Then using that, you create a kernel, which I just showed you. The kernel is launched by the CPU onto the GPU. So that's all this type does. It has one method, which is enqueue, which submits this program, which is your work, as a command to the GPU's command queue. And the GPU's command queue has these parameters. So as I said, you have all these threads, right? So you is still there, yeah. So you have all these threads, right? So you can say that in this thread box, this is actually a 3-dimensional thread box, where you're saying this thread is taking up this space, so it's 0, 0, 0. The ID of this core or thread is 0, 0, 0. The ID of this box or this core is 3, 1, 0. Then the ID of this box, which is at the back, which is in a three-dimensional fashion, you can say this is 3, 0, 1. It's basically IDs for your your actual GPU cores or ALUs that you have. Now the same thing is also applicable to blocks as well. You can also have blocks. So a grid of threads or cores make up a block. Then a grid or a collection of blocks make up a grid, right? So that's what you sort of specify over here, saying, okay, At the end of the day, here's how many threads I want you to spin up on the GPU and get this job done. Okay, and this enqueue method actually does that for you, right? Anyway, I'll sort of upload this to a repo so that you can also sort of take a look at this and share your thoughts as well. Once that is done, once I've submitted my work to the GPU, I do nothing. I'm done. I have no control over it. The GPU automatically goes ahead and distributes that work onto the respective cores, etc. You have no control after that point. Okay, everything's done by the GPU. What you do is you need to know when to read that data back. That means the result back, right? Now that's the part that gets very interesting. This is where the whole Rust piece comes into the picture, where you need to be sure that there are no synchronization issues between this GPU and the CPU. Because if you think about it, this buffer is now on the GPU, right? What I want is, I want the result. But I need to know when to read that result. So that I don't end up reading half the result or some garbage stuff, right? In order to do that, that's where you do something called mapping and unmapping of buffers. And let me actually walk you through this. So when you actually want to do mapping, forget all of this. What happens is, mapping a buffer basically means you're not actually copying the buffer from GPU memory to CPU memory. The buffer stays in GPU memory. All you're saying is the GPU is no longer going to use it. That's when I'm going to map it, which means I'm going to say that, okay, CPU, you now have access to my buffer that's present in my memory. I'm not going to use it. That way, none of us are, messing up what the other's done. All right. That's basically mapping. And that's the other part about the safe portable API, that's WebGPU. Previously, in other APIs, even if you use something like the native OS APIs, you would have to go ahead and take care of this yourself. Right? Does that make sense? Sorry, let me go back. Let me just check the chat. Does that make sense? Yep. Okay, that makes sense. All right, so that is technically what we call, that's technically what we need to do, which is map the buffer. And the way mapping actually happens in WGPU is very interesting. We have something called a lifetime tracker type, which I don't think I have time to go into. But basically, the lifetime tracker type tracks these resources and says, okay, you submitted this buffer in this command at this point. So let me just go check that command queue if it's still there. If it's not there, if it's still there, that means the GPU still needs it. If it's not there, that means the GPU is sort of done with it. And I can go ahead and unmap the buffer and you can start reading it, right? So that is sort of how the unmapping happens, and so that the CPU can read it. And then we return the result over here. So in this case, what I'm doing is I set up about 32,000 elements of the list that I have. I have 32,000 of them. And I'm basically, so the other thing that I've done is, we talked about Rayon just a couple of, the start of this session. Now, so I've got 3 implementations. One runs on GPU, which is this implementation. Then the other runs using Rayon, which is the parallel implementation. That means the data parallelized version. As you can see, the thing that is very interesting is, look at these 2 versions, right? They almost look similar. The only difference is I have this extra iter called par-iter, which is parallel iterator, right? It's actually really well done. If you look at both of them, there is nothing different about them, except for the fact that this is different. This iterator is it's not a parallel iterator. It's a straightforward regular iterator, and this is the parallel iterator, right? So effectively what a parallel iterator does is it distributes work across the different cores, much like what the GPU is doing, except it's on the CPU. This one does not do that. You're doing all of that work on the same core. Right. And then the GPU, as the architecture, as I've shown you, it does all of that for you, right? Now, so what I've done is I've put together some calculations to say, okay, how much time does it take to compute it on the CPU, running it parallelly on the CPU, and then doing it on the GPU. And then I'm just for ease, just for accuracy's sake, I'm trying to see if all the results are also the same. They're not, they're not garbage and stuff. All right, so let me just quickly run this so that, we can sort of have an idea of that as well. So I've already ran this, so okay. You notice something that's very interesting over here. The GPU takes about 27 milliseconds. The CPU, that too, the one that is not parallelized, takes lesser time. In fact, I've noticed that if I drop the number of elements, the CPU is much faster. The parallel one and the GPU are actually take a lot longer. Now, I think I may know what the reason is. It's possibly that we're not, we're not taking advantage of the real thing, which is providing more throughput. That is, you need more data elements to actually see the benefit of the GPU. That may be the first thing. Or second thing, you could probably you probably have to split your elements into smaller chunks and submit them all from different threads, so that you get the GPU to do all that work at once. That's possibly the other thing that I'm thinking. But anyway, those are the things that I think I still have to understand. But let's just try this. Let's just say I drop this to 10,000 and I sort of remove this. So if I were to do that, something very interesting just popped out. All right, so this is extremely interesting. This thing takes 320 microseconds. This is on the CPU. And when you do it parallelly, it sort of takes the same amount of time as the GPU. So what gives? I don't know. It doesn't make sense. Yeah, maybe we need to really learn more about this. So barring that part, which we need to get into a little more to sort of figure out why that's happening. And at least we can say that we've got basic GPU compute working using WGPU, the crate, and also sort of a basic understanding of WebGPU, the spec, and what is this whole compute thing about. Anyway, the other part is I'm going to be uploading all of this, putting all of this in a crate and just making it available so that you sort of have it with you to go through this. Yeah, so I just wanted to keep it short and not take up too much time, because yeah, the longer the stream, it's not helping people out. So anyway, any questions before we, for a break? That's hilarious, right? Why the hell? So my guess is the M1 Max, which is the Apple Silicon thing that I'm using right now, is probably wicked fast when it comes to single core performance. And it's well optimized for the computations like this. Of course, I don't think that it's faster than a GPU. I'm probably not really thinking about it correctly. That's my best guess. And we need to look at this a little more. Is it more data that we need to provide? Is it more work submissions that we need to do? What is it? That's a question, right? Anyway, that's a part that we can look at. Maybe maybe over the weekend. Yeah, that's what I can do. Yeah, maybe optimize. So the CPU, I'm presuming that it's extremely well optimized for this calculation. It's, I mean, 320 microseconds versus 30 milliseconds in this method for 10,000 elements it doesn't make sense. If that's the case, there's no point of a GPU. But yeah, let's not jump to conclusions. I'm pretty sure we need to learn more about this to sort of figure this out. Okay, any other questions? But yeah, that's the good point. So yes, when I keep increasing the number of elements, I see that the CPU gets slower. That single core CPU gets slower. For example, if I did something like this, where is that? You go back. I did something like this. By the way, I'm still yet to figure out how do I spin up more threads, because the only thing I've been able to do so far is 50,000. I'm missing something over there. That's another part. So let me just run this now. Okay, now you see. So previously the parallel, and that's the other thing. When you're doing parallel computation, it can be extremely unpredictable as well, right? Now it's almost the same, but the GPU still remains the same. That means we're definitely missing something, right? The GPU is very consistent, but the CPUs, the parallel workload versus the regular workload seems to keep changing. But one important point, this at least tells us something, that if you increase the number of elements in the array for parallel computation, then you start to see single core slowdowns, right? That makes sense, no? Okay. All right. So I guess that's it for this stream. And hopefully I hope this was informative, because we are going to be actually delving sort of deep, maybe not right away, but towards the later part of this year, maybe, into the GPU, specifically in the embedded context, for things like machine learning, etc., which we will talk about when we get to that. But this is a starting point. Okay, cool. That's it. And have a good day. Bye.